Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules.
Welcome to Lesson 19, Interpreting Correlation. Classwork Example 1, Positive and Negative Linear Relationships. Linear relationships can be described as either positive or negative. Below are two scatter plots that display a linear relationship between numerical values x and y. Okay. So move that up there. So what they're saying is there are linear relationships, positive and negative correlations. Positive we usually use green, so let's do this. So as you can see, a line of best fit might look something like that. These points are scattered around, but they're grouped fairly close to this positive sloped line. And this one over here appears to be going in this direction, down. So that's a negative linear correlation, and this is a positive linear correlation. Exercise 1. The relationship displayed in scatter plot 1 is positive linear relationship. Does the value of y variable tend to increase or decrease as the value of x increases? So as we are going to the right, 20, 30, 40, 50, 60, 70, 80, what is y doing? 5,000, 6,000, 9,500, over 10,000. So as you can see, as x increases, y is increasing. So it's increasing. It's a positive slope or a positive rate of change. Number 2, the relationship displayed in scatter plot 2 is a negative linear relationship. As the value of one of the variables increases, x, as x is increasing, what happens to the value of the other? It decreases. As y increases, x is decreasing, if you look at it that way. If you were to describe the relationship using a line, would the line have a positive or negative slope? So the first question asks, what happened to the value of the other variable? So as one variable increases, the other variable decreases, and that will create a negative slope or a negative rate of change. Okay, page 2 brings us to problem number 3. And it says, what does it mean to say that there's a positive linear relationship between two variables? So what you would say is, as one variable increases, the other variable also increases. So as one increases, the other increases. So putting it into words, we would say a positive linear relationship indicates that as the values of one variable increase, the values of the other variable also tend to increase. Number 4, what does it mean to say that there's a negative linear relationship between two variables? Okay, a negative linear relationship indicates that as the values of one variable increase, the values of the other variable tend to decrease. So as one goes up, the other goes down. That makes a negative relationship. Okay, example 2. Some linear relationships are stronger than others. Below are two scatter plots that show linear relationships between numerical variables x and y. Is the linear relationship in scatter plot 3 positive or negative? So in other words, if I were to take a line and draw it in, where would that end up? Would it be here? Would it be here? Would it be down here like this? Does that fit well? There tends to be a lot of distance between here and here, or I should say here and straight down here, here and here. Big difference here. So if I rotate this around and move this line so that these points are somewhat close to this line, okay, this one's still kind of far away, but notice these are a lot closer. This one's close, fairly close. This one's close. These are close. This seems to fit better here. So there is the linear relationship in scatter plot 3 positive or negative? I would say it's positive. As x increases, the y values tend to increase. Okay, so in general, there are more points in the scatter plot that describe a positive relationship. Number 6, is the linear relationship in scatterplot 4 positive or negative? Again, if I choose a line segment, let's just use the same color here, it tends to fit right here. This is a better fit than this one over here. This is a stronger relationship than this, because the further the points are from the line of fit, the weaker the relationship. So this is a weak positive linear relationship. This is a stronger positive linear relationship. So this scatter plot also indicates a positive relationship. For most of the points, students should note that as the x values increase, the y values will also tend to increase. Okay, page 3 brings us to problem number 7. It is also common to describe the strength of a linear relationship. I've already been stating that in the last couple pages. We would say that the linear relationship in scatterplot 3 is weaker than the linear relationship in scatterplot 4. Number 7, why do you think the linear relationship in scatterplot 3 is considered weaker than the linear relationship in scatterplot 4? So I explained this in detail already, so I kind of got ahead of myself, but here's what we would say. Okay, students should comment on the general scatter of the points. So you should comment that some are scattered further away from the line of fit. You should say something like that. So the points in scatterplot 3 are more scattered and do not cluster tightly around a line, while in scatterplot 4, the points conform more closely to the line. Number 8, what do you think a scatterplot with the strongest possible linear relationship might look like if it is a positive relationship? Draw a scatterplot with 5 points that illustrate this. Okay, so the strongest possible linear relationship would be points. These 5 points would be right on the line, so that there would be no distance between the predicted and the actual. The actual would be on the predicted line. So the easiest way to draw this would be to draw a line. I'm going to make it thin. Draw a line segment like so, and then put the dots on that line. So here's 1, here's 2, here's 3, here's 4, and here's 5. Okay, so what that would mean is, let me just delete this now. So there is a perfectly straight line with 5 dots on it. So what that would mean is the slope or the rate of change would be equal between each point. So if I went up 1 over 2, it'd be up 1 over 2, up 1 over 2, up 1 over 2, and so on. Okay, so that's what it would look like if it was the strongest possible positive relationship. Number 9, how would a scatter plot that shows the strongest possible linear relationship that is negative look different from the scatter plot that you drew in the previous question? Okay, before I go any further though, let's go back to 8, and we should say something about the plot rather than just showing a plot. A scatter plot that has all the points on a line with a positive slope indicates the strongest positive linear relationship. So students should draw points that form a line with a positive slope. So there it is right there. Now let's do the same thing we did before. We want a very strong negative relationship. So the first thing I would do is draw a line segment and then choose a color and plot points that are right on. Hello? Choose points that are right on this line. And they can be anywhere. There can be a distance between them. They don't have to be equally separated. I could put one way down here. Okay, and then I would delete my line. So if you just used a ruler and put dots on your paper, that would be perfect. So there it is. That's what it would look like. The strongest negative linear relationship would be 5 points right on a line. So now we would say a scatter plot with the strongest possible negative linear relationship will be one in which all of the points are on a line with a negative slope or rate of change. This line has a negative slope, while the line drawn in exercise 8 would have a positive slope. Okay, page 4 brings us to an exercise. So try this on your own, pause the video, then come back and see if you did it correctly. Okay, here we go. Exercise 10 through 12, strength of linear relationships. Consider the three scatter plots below. Place them in order from the one that shows the strongest relationship to the one that shows the weakest linear relationship. So we're going strongest to weakest. So if I look at these, what you could do is just take a ruler on your paper and draw a segment like so, and arrange it so that it appears to have a fairly strong relationship here. It might look something like this. So these points are really close. This one's a little high, but it's almost the same distance as this is low. So this would look kind of like where the linear relationship would be. Three of the points are very close, and there's a couple outliers. Now let's do the same for the next one. And this one here, there's a point here, and there's points here, so it kind of tends to be positive here, but there's an outlier up here that's kind of far away, and these two are a little bit further away. So this would kind of look like where it would be. Maybe this end would be moved up a hair like that, so somewhere around there, without plugging these exact values in and checking with a calculator, or doing it manually, which we have not done yet. That's the only other way we could draw this line accurately. And then finally on this last one, I would say it'd be just about like that. These 3 points are almost right on, one above, one below. That would average out so that these, so there's the 3 lines. Now we need to answer the question. Which one has the strongest linear relationship? In other words, which one has points that are closest to the line? And I would say number scatter plot 7. And then to the weakest. So I would skip the middle one and I'd go right to the weakest. This one's still fairly strong. These 3 points are a little further away, but this one has 2 points that are really far away. So I'd say 5 was the weakest. And therefore the process of elimination would leave the middle man 6. There it is. So it goes from strongest 7, 6 to the weakest 5. Now 11 says to explain your reasoning for choosing the order in exercise 10. So I already explained my reasoning as I was doing this, but here it is in words. Okay, so you should imagine there is a least squares line in each plot, which I did. The strongest linear relationship has the smallest sum of the squares of residuals, while the weakest linear relationship has the largest sum of the squares of the residuals. Okay, page 5 brings us to problem number 12. It says, which of the following 2 scatter plots shows the stronger linear relationships? We need to look at this really closely. This is 0, 10. And if you look at this, if you just flip this over, there's a mirror image. If I drew a line of reflection right here, straight up and down, then these points would just flip over. So if I drew a line of fit, it might look somewhere like this, where these 2 points are below, this one's above, and these 2 are pretty close. So with that being said, I might draw this one this way. And as you can see, these points are the same distance away, because this value here is 10, 60 something, and this one's 50, 60 something. So these values, these y values are equal, and the x values are just reflected, and they're of a distance of like 40. So they're just flipped over. It's a reflection. So these have the same strength. Just because one's negative and one's positive, positive does not mean that it's stronger. Just keep that in mind, and that's what they're trying to explain here. Okay, so the strength of the linear relationship is actually the same for each of these examples. The difference in the scatter plots, however, is that scatter plot 8 indicates a negative linear relationship, and scatter plot 9 indicates a positive relationship. Note that it is important to discuss this response with students if the question is not answered correctly. So if you didn't answer correctly, hopefully my explanation cleared this up. Example 3. The correlation coefficient. Okay, there is a new vocabulary word. Let me underline that. The correlation coefficient. Not a very good color. Let's try that again. Correlation coefficient is a number between -1 and +1, including -1 and +1, that measures the strength and direction of a linear relationship. The correlation coefficient is denoted by the letter R. Several scatter plots are shown below. Probably on the next page, I guess, because there's only one here. The value of the correlation coefficient for the data displayed in each is also given. So this one is linear, and the R equals a +1. And the reason it's at its maximum, because that's the maximum, right? It's between -1 and 1 inclusive. And the reason that is because if I put my cursor here and drop that there, these points are right on the line. That's as strong as you can get. That is an R value of +1. Okay, page 6 is a continuation. So we're looking at scatter plots with a given correlation coefficient. And in this case, R is 0.71, and it's positive. So the positive value is going to tell us that it has a positive correlation. 0.71 means that it's 1.00 is 100%. 100% of the points are on the line, if you will. 0.71 is fairly strong, and then when you get to 0, that is the weakest it can be. 0 means there is no correlation whatsoever. It's just a scatter, a mishmash of points all over the place with no shape or form. Okay, so here's 0.71. Fairly strong, 0.71. 0.5 would be a middle of the road, so that'd be like a moderate correlation, positive. And then as you go closer to 0, between 5 and 0, or I should say 0.5 and 0, you're going to say it's a weak positive or negative linear correlation. So 0.71 is a fairly strong positive correlation. Okay, this one is positive as well, so that indicates that we're going to draw a line with a positive slope like so. This is just an approximation, by the way, of what it should look like. This is really far away. These 2 points are kind of far away, and these 2 are about the same. Okay, so this would be a positive correlation, but it's a weak positive correlation because it's less than 0.5, I would say. And then now we have a negative R value. Well, a negative R value is going to tell us that we have a negative relationship, but it's very weak. Okay, it's close to 0. So these points are really far away. And I'm not even sure if this is what it would look like. It might be a rotation. We might have to rotate that some way, like so. Maybe like that. Okay, but without really doing any calculations, it's hard to estimate exactly where it would be. Let me just put my cursor back here. Okay. So, recapping this page. Positive, moderately strong correlation, positive weak correlation, negative weak correlation. Okay, page 7 brings us to 3 more examples, and we're going to continue with what we've been doing. So let me just draw lines, just to give us an idea of what we're doing. So this is a negative, so I'm going to start up here and work my way down, but where is it going to end up? Okay, that's definitely not it. Maybe somewhere around here, so that these distances average out. That's a least squares regression line does. And a negative correlation means that it's downward slope. And 0.32 is a moderately weak correlation. Okay, now this one here is a negative 0.63. So if I started up here somewhere, or maybe down here and went this way, then maybe it would be somewhere around here. So in this case, these 3 points are really far away. This is kind of far away, and this one's fairly close, but on average, they're pretty far away. So this is a weak negative correlation, or moderately weak correlation. And then this last one, if I put my point right there and drag this right there, all those points are right on that line. That's the strongest it can be. That is a -1. Very strong negative correlation. Okay, page 8 brings us to exercise 13 through 15. So pause the video, answer these questions. Unpause the video, and we'll check, see how you did. Okay, so here we go. So, number 1, or 13. When is the value of the correlation coefficient positive? And the answer is the correlation coefficient is positive when, as the x value increases, the y value also tends to increase. They're not asking about strength here, just when is it positive. Number 14, when is the value of the correlation coefficient negative? Okay, the correlation coefficient is negative when, as the x values increase, the y values tend to decrease. Number 15, is the linear relationship stronger when the correlation coefficient is closer to 0 or to 1 or -1? Okay, so as the points form a stronger negative or positive linear relationship, the correlation coefficients gets farther from 0. So you should note that when all of the points are on a line with a positive slope, the correlation coefficient is a +1. The correlation coefficient is a -1 if all of the points are on a line with a negative slope. All right, looking at the scatter plots in example 4, you should have discovered the following properties of the correlation coefficient. Property 1, the sign of r, positive or negative, corresponds to the direction of the linear relationship. Property 2, the value of r equals a +1 indicates a perfect positive linear relationship with all points in the scatter plot falling exactly on a straight line. Property 3, a value of r equaling -1 indicates a perfect negative linear relationship with all points in the scatter plot falling exactly on a straight line. And property 4, the closer the value of r is to +1 or -1, the stronger the relationship is. Okay, so now page 9 brings us to calculating the value of the correlation coefficient. Okay, so we've been talking about it, so now we're going to figure out how to calculate this thing. Now, if you haven't noticed, or maybe you have in the last few lessons, when I do a linear regression in my calculator, and I go to y equals, there's probably one already there from a prior lesson, and there it is. And if I go to plot 1, because I don't want the residual, which is what this is being plotted, so I'm going to turn that back off, and I'm going to turn on my equation, and then I'm going to zoom 9. So there's my linear regression that we did recently, and if I go to stat, calculate, lin regression a plus x plus b, that's number 4. Or there is another one where it is a plus bx. If we use this one, then we L1, L2, store reg EQs, we just enter through here. And I'll explain this before I continue. Now there's an R2, R squared, and an R. All right, so there's our R. There is our R. That is the regression. Look at how strong this is. Positive 0.999. That's pretty darn close to 1. And when I look at the graph, sure enough, these points are almost on a perfectly straight line. Okay, so we're going to go through that again when we do one of these problems. So until then, I'm going to clear all my information. So let's go through clearing everything now. So I'm going to clear my equation. I'm going to go to stat, enter, and see that there's data there from the last problem. So to clear that, I'm going to press stat. Number 4 is clear list, and it's asking which lists to clear. Well, those were L1 and L2, and you see these are in blue, so that means press the blue button to get the command above number 1. Put a comma between it. You can do these at the same time. Second L2, and hit enter, and it says done. Now if I go to stat, enter, my L1 and my L2 are blank. All right, I'm going to zoom 6 just to, okay, and it says invalid dimensions because I have is quit, enter, clear. Y equals is blank, my plot's on. Let's turn that off and see what that does. Second graph, that's blank. So now if I zoom 6, it should be okay. All right, there it is. So this is just negative 10 to 10. This might be where your calculator is. I wanted it there because that's generally where they are when you start, especially when you share a calculator in a classroom with different courses. Okay, so example 4. There is an equation that can be used to calculate the value of the correlation coefficient given data on two numerical variables, bivariate data. Using this formula requires a lot of tedious calculations that are discussed in later grades. Fortunately, a graphing calculator can be used to find the value of the correlation coefficient once you have entered the data. Your teacher will show you how to enter data. I will show you how to enter this data now in this video and how to use a graphing calculator to obtain the value of the correlation coefficient. So here is the data from the previous lesson on shoe length in inches and height in inches for 10 men. But before I go any further, inquiring minds want to know. I always love to give information to students who are just hungry for information, and some people might not be okay with just letting this go by. They might say, I don't want to wait until later classes. I want to know what that equation is. I want to see if I can figure out this manually without the use of a calculator. So I'm going to give you the equation to find R. Okay, for those of you who are interested, this is the equation for R, and you might think, oh my, I would never be able to do that, don't even know what that means, but it's actually pretty simple. In parentheses, in the numerator up here is x, and then x with a line over top is called x bar, and that just means the mean, the average. So you have 12.6 and all these points right here. So what you would do is take this plus 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 this and divide by 10, and that would give you the average. Then you would take 12.6 and subtract the average and get a number. Do it again for all of these. And this sigma, capital sigma, Greek letter, means the sum of. So you're going to take all the sums of x minus the mean, x minus the mean, all those values you got, you add them up, and that gives you your numerator. Then down below, you're going to take the sum of all those x minus x bar means, and you're going to square them, and then you're going to take the square root of the sum of the squares. And then you're going to do the same for the y's. So you're going to find the average of the y's, take y minus the mean, 65 minus the mean, 71 minus the mean, 67 minus the mean, take the sum of all of those and square them, and then take the square root. Actually, you're going to square them first. So say this was 72, so you'd say 74 minus 72 is 2. 2 squared is 4. So then you would take all the squares, the sum of all those squares, y minus y2, or y minus y mean squared, and take the sum of all those squares. And then you multiply those two, and then so that's this divided by those. So anyhow, for those who are interested, that's that. Now let's move on to exercises 16 and 17. We're just going to use the calculator now. We're not going to do this manually. So it says enter the shoe lengths and the height data into your calculator. Okay, so let's do that. Here's my calculator. And so we're going to go to stat, edit, and we're going to enter this data. So 12.6, 11.8, 12.2, and I put 1, 12.2, 11.6, 12.2, 11.4, 12.8, 12.2, 12.6, and 11.8. And as I always do, I go up 1, and it's telling me that there were 10 entries, and I already counted these. There is 10. Arrow over to L2 and plug in our y's. 74, 65, 71, 67, 69, 68, 70, 69, 72, 71. Okay, make sure that you have the same number of L1s as you do L2s, or you'll get an error, mismatch. All right, so we've entered the shoe length and the height data into our calculator. Check. Find the value of the correlation coefficient between shoe lengths and height, round to the nearest tenth. Okay, so we've entered our data. Now we're going to find the linear regression. We're going to go stat, calculate, arrow down to 8, linear regression, a plus bx. We can use ax plus b, but we're going to use a plus bx. I'm not going to explain that now. And I hit enter. Make sure x list is coming from L1, y list coming from L2. These we can just leave blank and enter through. And hit enter. Our slope or rate of change is 25.28. Our y-intercept was 3.66, and our r is 0.65. So is this a positive or negative correlation? A, it's positive. 0.65 is positive. Is it weak? Is it moderate? Is it strong? 0.65 is more than 0.5, which is the middle of the road. This would be a moderately strong correlation. Positive, by the way. Okay, so we found the value of correlation coefficient between shoe length and height, round to the nearest tenth. So I would say R equals 0.65, right? Because before we round down. Okay, so it's 0.65. Oh, it says the nearest tenth, not hundredth. So that would be 0.7. My apologies. 0.65 rounds to 0.7. Okay, 0.7. Okay, let me fix this though. I don't want equals, I rounded. Okay, this should be approximate. R is approximately 0.7. The table below shows how you can informally interpret the value of the correlation coefficient. So here it is, R is perfect. So we have a 0.7. So R is greater than or equal to 0.7 but less than 1. This is a strong positive linear relationship. I would go 2 decimal places personally, and I would see 0.65, and I'd say, well, that's less than 0.7, so I'd say moderately positive linear relationship. Okay, I'm not really, if you're going to round, 0.65 is less than 0.7, so it doesn't fall in here, right? So I'd say this is more moderately, it's on the border of moderately positive and strong positive. So it says, okay, that's it on this page. Okay, page 10 brings us to number 17. Interpret the value of the correlation coefficient between the shoe length and height for the data given above. So, based on the table, there's a moderate positive linear relationship. Connecting this to the scatter plot provides an example of a moderate positive linear relationship. Okay, so it says connecting this to a scatter plot, but we haven't done that. So So I've already done my linear regression, and I found my rate of change and my y-intercept and my correlation coefficient. So now let's just go to y equals, turn our plot on, press vars, 5 for statistics, EQ, enter, and it's in there now, zoom 9 for statistics, and there's the scatter plot with the positive correlation coefficient being 0.65, going through the data. See, these points are fairly strong. It's a moderately strong positive correlation, and you see that in the graph. Okay, exercises 18 through 24 says to practice calculating and interpreting correlation coefficients. So this is a practice, so pause the video, see if you can do this, and then come back and check. So here we go. Consumer Reports published a study of fast food items. The table and scatter plot below display the fat content in grams, the number of calories per serving for 16 fast food items. Okay, so based on the scatter plot, do you think the value of the correlation coefficient between fat content and calories per serving will be positive or negative? Explain why you made this choice. Okay, so to answer this, I would see if I could draw a line of fit through it. And I would say it would be something like that. Not exactly probably, but close. But it does appear to be a positive correlation. So this is just asking, will it be positive or negative, and explain. So I would say positive. The general pattern is that as the fat content increases, the number of calories tends to increase. Okay, page 11 brings us to number 19. Based on the scatter plot, estimate, okay, estimate the value of the correlation coefficient between fat content and calories. I am not going to tell you what I would estimate because everybody sees things a little differently and interpret things different ways. So we would need a range of answers here based on someone's argument. So here's what I'm going to say here. The scatter plot appears to have a positive correlation coefficient, but it also does not appear to be a strong relationship. Those points are not right on the line. As a result, students would indicate a moderate positive linear relationship and might predict a value between 0.3 and 0.7. So there's a range there. Now number 20 says to calculate the value of the correlation coefficient between fat and calories per serving and round to the nearest hundredth. So now they want us to actually find it. So we're going to go back to the data and we're going to enter that in the calculator. So I'm going to go to y equals. I'm going to clear that. I'm going to go to stat, enter, and now I want to enter this data here, and there's stuff in L1 and L2, so press stat, clear list is number 4. We want to clear L1, comma, L2. Enter. Now go to stat, edit, enter the data. Fat in grams is X, so that's 2, 5, 3, 3.5, 1, 2, 3, 6, 3, 5, 3.5, 2.5, 0, 2.5, 1, 3. Okay, I ended up, my cursor is on the last number, 16 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, arrow over to L2 and enter the calories. 268, 303, 260, 300, 315, 160, 200, 320, 420, 290, 285, 390, 140, 330, 120, and 180. And then make sure you have the same number L1 and L2. If we don't have them, you get an error or mismatch. Okay, so that's done. Now we go to stat, calculate. 8 is the number you want to use for this linear regression, a plus bx. Hit enter. L1, L2, very good, enter. And there is our R, 0.44. Okay, so now move back to the page we were on. Round to the nearest hundredth. 0.441 would round to 0.44. So I'm going to write that as an approximation. I would say R is approximately 0.44. Go back to my table, 2 pages back. 0.44 is right here, between 0.3 and 0.7, so it is a moderate positive linear relationship. Okay, so you would say the correlation coefficient is R is approximately 0.44. It indicates a moderate positive linear relationship. So please use that table when you're doing your homework because you will need to know what's moderate, what's strong, what's weak, what's positive, what's negative. All right, the Consumer Reports study also collected data on sodium content in milligrams and number of calories per serving for the same 16 fast food items. The data is represented in the table in the scatter plot below. 21. So here's the scatter plot. So if I were to draw, just without even reading the question, if I were to just draw a regression line, it might be somewhere around there. It is positive. Is it strong? Is it weak? Is it moderate? Based on the scatter plot, do you think the value of the correlation coefficient between sodium content and calories per serving will be positive or negative? Explain why you made this choice. So I would definitely say it's positive. Okay, and the reason is, as X increases, so did Y. Positive, as the sodium content increased, that's X. The number of calories tended to increase, that was our Y. X increases, Y increases, positive correlation. Okay, page 12. Whew, 12 pages in a lesson, wow. Page 12, number 22, based on the scatter plot, estimate the value of the correlation coefficient between sodium content and calories per serving. So now again, we are estimating. I go back, I look. Here's sodium, here's calories, there's the correlation. That looks fairly, it's positive, it looks fairly strong. So I might choose, if I go back to my table here, right here, let's erase this mess. Okay. What do you think it might be? Well, if you think it is a strong positive linear relationship or moderate, you might choose something around 0.7, 0.75, somewhere around there, based on, depending on what you believe it to be. So, this is an assumption, this is an estimate, this is someone's opinion, so there's going to be a window of answers. So I would say this relationship appears to be stronger than the previous example. An estimate of the correlation coefficient is between 0.7 and 1. Number 23, calculate the value of the correlation coefficient between sodium and calories per serving. Round to the nearest hundredth, interpret this value. So now we're going to enter this data here. Okay, so I go to stat. Now remember, there's stuff in there from our last couple problems, so we want to clear the list. And we're going to do second L1, comma, second L2, enter, stat, edit, and it's blank. Now we have to enter this. So here we go. Should have played some music in the background while I'm doing this. Okay, 268. Okay, so I look, make sure that there's the same number. There's not another one down here or another one down here with nothing next to it. So there's no mismatch error. There are 16 entries. There are 16 here. Always check that. Now that that's entered, you press stat, calculate 8 for A plus BX, L1, L2, and we get R to be 0.786. It said to round to the nearest hundredth. That'd be 0.78, and this 6 makes that a 9. So my estimate would be R is approximately 0.79. So the correlation coefficient is R is approximately 0.79 by the table. Let's go back a couple pages. 0.79 is between 0.7 and 1. So that is a strong positive linear relationship. Just showing where that came from. By the table, this indicates a strong positive linear relationship between sodium content and calories. 24. For these 16 fast food items, is the linear relationship between fat content and number of calories stronger or weaker than the linear relationship between sodium content and number of calories? Does this surprise you? Explain why or why not. So now it's really easy to see which one has a stronger relationship by just looking at the value. The salt had a 0.79 R value, and the fat content had a 0.44 R value. Well, 0.79 is more than 0.44, so salt is more of a reason for caloric increase than fat is. Does that surprise you, is what the question's asking. The linear relationship is stronger for the sodium content in calories. So the answers will vary as to whether or not this would surprise a student. It is anticipated that many students would think that fat was more strongly correlated to the number of calories. A summary to help explain this is provided in the next example. Example 5. Correlation does not mean there is a cause and effect relationship between variables. It is sometimes tempting to conclude that if there is a strong linear relationship between two variables, that one variable is causing the variable of the other variable to increase or decrease. But you should avoid making this mistake. When there is a strong linear relationship, it means that the two variables tend to vary together in a predictable way, which might be due to something other than the cause and effect relationship. Do not ever say this caused this to happen. For example, the value of the correlation coefficient between sodium content and the number of calories for the fast food items in the previous example was R equals 0.79, indicating a strong positive relationship. This means that the items with the higher sodium content tend to have a higher number of calories. But the high number of calories is not caused by the high sodium content. In fact, sodium does not have any calories. What may be happening is that food items with high sodium content also may be the items that are high in sugar or fat, and this is the reason for the higher number of calories in these items. Similarly, there is a strong positive correlation between shoe size and reading ability in children, but it would be silly to think that having big feet causes children to read better. It just means that the two variables vary together in a predictable way. Can you think of a reason that might explain why children with larger feet also tend to score higher on reading tests? Leave that to you. Okay, page 13 brings us to the end of a lengthy lesson 19. Review the lesson summary and go to your problem set.